Okay, so related rates, we're going to continue with it. We did the latter one. This one's going to be a cone one. And if you look at it, looks like a lot of geometry. And some of the formulas are like geometry formulas that you're going to use with volume and circumference, in this case, radius and height, and the volume of a cone on there. So let's look at exactly what's happening here. So here's the volume, and we want to know what the water level is changing on here and how we're going to find at what rate we're going to do that. So if I look at this, I have water pouring into this cone. So I have water pouring, and then it gets increasing until it actually fills up. So we're going to be able to figure out quite a few things from here. And so if I start here, there is a relationship here. I have the radius and then the height, and as it gets filled more and more with water, it's going to get the radius gets closer to 4, and then the height is going to be all the way to 10. So right now, if I actually look at it, because of the way the cone is shaped, I have this here that it's going to be proportional triangles. So they're going to be R is proportional to 4 as H is proportional to 10. So as H and R are growing, they're growing the same way all the way up till they get to the top on there. And so that's what you're seeing on there. So it's getting filled or it's losing water or getting filled on there. And so the relationship between R and the full tank and H and the full height, that's what we're going to use to help us use calculus to figure out everything in between, and the rate that the volume is falling, the rate that the radius is changing, the rate that the height is changing, all that wonderful stuff there. So when we go back, this is the same example that we talked about, R and H, and then 4 and 10. So what is the relationship between the height of the water and R, the radius on there, so the top on there? So we want to know the relationship that we have there. So we said that they're similar triangles, which is we're going to stick to that because it's true. And so I know that when we have um, similar triangles, we're having that they're going to be proportional. That means that their fractions are going to be the same on there. So they're going to be the same. Example here is that if I show that R is the radius to H, we know that it's going to be similar to 4, the final one, and then H is going to be 10. So R and H is anything in between, and it's going to be similar to the big triangle of 4 and 10. And of course, we don't always have to just do that. We could do it the other way around, and we could have H is to R, H is to R as 10 is to 4. They're proportional. One fraction equals to another fraction. Now, because we have one fraction equal to another fraction, and there's an equal sign equal on there, that's when you could do cross multiplication. You cannot do cross multiplication, and a lot of students confuse it if there is a multiplication symbol in there instead of an equal sign. Here we can, and so we know that we get 10R equals to 4H. And so I could solve for R, and I get that R is going to be 4 over 10H. And same thing over here. I could have this to be, we do the same thing, and you end up with 4H is equal to 10R. And so we end up with H is going to be 10 over 4R. And then, of course, you could always reduce your fractions on there. And so if I actually do reduce my fractions, I am going to get 2/5. And same thing on this one here, we're going to get, I'm just going to erase this and then just write 2/5 R. Okay, so that's how R and H is going to be related, and we're going to use that often on there. You need to know the relationship between the two variables on there. So now we're going to write a formula for the volume of the water as a function of H. So when it says it's a function of H, that means that we are going to get the volume, which is as a function of H, is going to be, we want to know what V of H is. That means that everything after it has to have an H. It cannot have an R in it. So the only thing we want is H in this formula. So we're going to use this information. Well, the volume for a cone, if we write, I'm going to write this down in color here. The volume for this cone here is going to be 1/3, one Oh, my computer's not nice right now. I don't know why it's acting up. Let me hit escape a couple of times. Hopefully that'll do it. 1/3 um, pi r squared h. So that's the volume of a cone. So that's what we're going to use on there. So notice a couple of things. Pi is a number. So 1/3 is a number. So instead of writing the 1/3 pi, which we're so used to seeing, I would prefer to change that and put in pi over 3. Because if you do that, then you know that that's going to be the coefficient. And the only things that are variables are the r and the h. The r is being squared, which is the radius, and then the height, and then this is the coefficient of pi over 3. It makes it much nicer to do. So the goal here is that I want this formula of volume to only have h. I need to get rid of that r. So in order for me to do that, I already know the relationship between r and h for this cone that I have here that's being filled with water, and I know the relationship either way. So in this case here, I want to get rid of the r, so I am going to use this, and I know that r is 2/5 h. So I'm just going to use this and put in, let's see, I'm going to do that. Doesn't really matter. V of h is going to be pi over 3. I don't want the r, so I'm going to replace the r with 2/5 h, and I am going to square it, and then I have an h there. And then I'm just going to do the calculation, so it's going to be v of h is equal to pi over 3 for 25ths h squared h. And so that's what we're going to get when we square that. And so my v of h, notice how there's only h's now, is going to be 4 pi over 75 h cubed. And so that's what I end up with. So that is the formula of the volume as a function of h. Now, I am going to calculate the dv dt of this. So I am going to calculate this, the derivative on there. And so when I do that, I am going to get dv, so I don't need the h there anymore. I'm just going to take the derivative of v with respect to t. So I'm going to get dv dt just from this part right there. And then I'm going to take this. Now this here is just a coefficient. So I'm going to leave that alone and do the pi over 75. So that's just a coefficient. I'm going to leave it alone. And I am going to take the derivative of the h, and we're doing it with respect to time. All of this is as time is passing. The cone is getting filled as time is passing. And so that's why that's the t, and that's where we get the t. So we're going to do the same thing. So it's a little bit of implicit differentiation. We take the derivative of the outside, which is going to give me 3. I leave the inside alone, and then that's going to be squared, because that's what we get there. And then I take the derivative of h, and so that's going to be dh dt, and that is going to be my derivative there. So the derivative here is going to be dv dt. This is over 1, so that means that I am going to multiply this, and I'm going to get 12 pi over 75, and then it's going to be h squared dh dt. So that's the derivative with the function of just h. But that's only good if I know h. If I don't know h, what if they gave me r? What am I going to do if that's the case with r? Well, if that's the case with r, that's what we're going to do next. We're going to write a formula for the volume of the water as a function of r. So what you do here is you're going to do the same thing that we did up here, and what we want is v of r. And so that's what we want to find out there. So the formula is still going to be v of r, and it's still going to be pi over 3. But when we look at the formula here, oops, when we put the formula, I want to keep the r, I just want to get rid of the h. So what does h equal? That equals to 2/5. I'm sorry, that is not 2/5 there. That's a mistake. That is going to be 5/2. Luckily, we caught that before I put it in. 5/2 of h. So we're going to have r squared times, and then we're going to put in the h, so it's going to be 5/2 r. And so that's what that is going to give us there. And so now I want to calculate it out and then give v of r is going to be, that's the coefficient, numerator to numerator is going to give me 5 pi, and then over this one here is going to give me 6. Very good. And then we're going to get r cubed. So let's just make sure that's right. So that's going to be 5/2 r, and that's h. We put that in there, and we're going to get a 5 and then 6. Okay, that looks good. Okay, so then we are going to do 5r, and then well, that's all we really need to do there. So we don't need to go anywhere else on that. That's what the volume is with respect to r, as a function of r. And so not with respect to, but as a function of r. There's only r's, there's no h's. So then we're going to go back over here, and then we are going to calculate the dv dt. So we're going to calculate the derivative of this one here. And the way that you do that is that we're going to take this and we're going to have dv dt. This is a coefficient, so we leave it alone. And then we take the derivative of that, so that's going to be 3r squared times dr dt. And then when we have this, it's going to be dv dt. That is going to be, this is over 1, so we're going to have 15. Well, actually, we could actually reduce this, right? Because it's just like reducing a fraction. And so I know that I could reduce that, and that's just going to be 2. So make it much easier for us. We're going to have 5 pi over 2. And then we're going to get, when that cancels on there, then this is going to be r squared dr dt. And that is the derivative of just using the volume, the dv dt and the dr dt. Okay. And so that's we'll be at this point there. Then if we know the radius or the rate at which the radius is changing, we could fill this out and we could find out what the volume is, how fast the volume is changing when the radius is 5 inches or whatever it is. Over here, this derivative here tells us that if I know the information about h, so if I know like maybe that at when h is 3 inches high, and I know the rate at which the height is changing, I will also be able to find the volume and how the volume is changing. So you would need to know the rate at which the height is changing and the height at that time, and or how the volume is changing, what the height. You just need one unknown. So we treat this as a variable, treat this as a variable, and treat that as a variable. Same thing here. This is a variable, this is a variable, and that's a variable. This is just a rate, this is a rate, and then this is just the actual radius at that time. Okay, so now we're going to translate some things into math language using the derivative. So if the information, and you're going to have to like write sentences for this on here. So if I'm looking at this and it says the height of the water is increasing 7 inches per minute. So we are going to translate that. And so now we know that the height is increasing. So we know it's a rate. So we know that this one here is going to be let me see. I'm going to choose this one here. So we know that the height is going to change. So we know it's going to be dh dt, because always with respect to time, especially because they're giving us 7 inches per minute, which is your time, and it's increasing. So we know it's going to be a positive 7 inches per minute. So that's how you change that. Translate the radius if the surface is decreasing 2 inches per minute. So if I'm looking at this, so we want to know the radius if the surface is decreasing. So we know that the radius is going to be decreasing because the surface is getting smaller, therefore the radius is getting smaller, and it says that it's decreasing there. So we're going to say dr dt is equal to -2 inches per minute. Okay. And then translate the math language. Water is pouring into a cone at a steady rate of 5 inches cubed per minute. And so that brings me back to the units. Units are so important. So this one here gives me inches per minute. And notice how it's just inches, inches not being squared, inches is not being there. So we know that this here is just going to be a height. It's talking about a distance height there. And then this is the radius. It's just inches. So it's going to be radius on there. And so now here, notice how water is pouring into the cone at a steady rate of 5 inches cubed per minute. So what are we really talking about here? R is measured just with certain length. Height is measured in certain length on there. And so it's just going to be inches and inches. The minutes is the rate at what the time is there. And so this one is giving us inches cubed, not inches squared, not inches. So when it's inches cubed and we don't know what it's talking about, the inches cubed tell us that it's the information. So volume is always going to have units cubed, area is always going to have units squared, and a distance like a radius or a height is going to be just straight inches. And so when we're looking at this, we are talking about that it's going to be dV dt because the units tell us so. And it's saying here that the water is being poured, so the volume is increasing. So therefore, it's going to be a positive inches cubed per minute. So make sure units have always been important and they're more important now when we're doing this. Make sure that you look at the units to get some information and that they match. Okay, very good.